Swayam Prabha. Digital India. Educated India.
In the last lecture, we were talking about some mathematical models for facility location. Today, we are going to be talking about the problem of layout planning, which, as you know, if you recall the hierarchy of location problems, is the next important problem where the objective is to determine the relative positioning of different departments. So in this lecture, we look at the basic issues that are involved in the layout planning exercise, and we look at a generic procedure known as systematic layout planning to develop a layout of a plant. What are the objectives in plant layout? When you develop a layout for a manufacturing plant, what are the typical objectives? There could be many objectives. Some of them are listed on this slide. For instance, one objective could be to minimize the investment in equipment. Now, somebody might say, how will a layout influence the investment in equipment? Obviously, if you don't duplicate equipment and you have a streamlined layout, then you would minimize the investment in equipment. So the layout has a considerable effect on the investment in equipment. It also helps you to minimize the overall production time. You can utilize the existing space most effectively with a proper layout. A proper layout should provide for employee convenience, safety, and comfort. You should try to maintain flexibility of arrangement. A layout generally tries to minimize the material handling cost. It also tries to minimize the variation in types of material handling equipment. For instance, a good layout would try to standardize the kind of material handling equipment that it uses. For instance, you don't expect forklift trolleys of very different sizes to operate in the same shop floor. You would expect standardized equipment. Generally, the plant layout would facilitate the manufacturing process, and it would also facilitate the organizational structure, because what would happen is that you are trying to place different kinds of equipment and trying to segregate different types of operations, and therefore it will tend to facilitate the organizational structure as well. Let us have a brief idea about different types of layout. Broadly speaking, we can talk about a product layout, a process layout, or a mixture of these two, which is called a mixed layout, or a layout by fixed position. Let us see, for instance, as to what are the features of each of these different types of layouts. A product layout is essentially one where a product enters the line on one side and you keep on performing different operations on the product till finally the finished product comes out on the other side. So all assembly lines, for instance, are typical examples of product layouts. The idea here is that the layout is dictated by the product. Whatever operations are required on the product, they are laid out in either straight line or in U mode or in serpentine mode or in any other mode, but the essential thing is that all the operations that are to be performed on the product are performed in sequence, and from the raw material you ultimately get the final product. So this is the typical feature of a product layout. In fact, when you are talking about product layouts, you tend to generally resort to product layouts when the volumes of production are large and like you have, for instance, and you have a dedicated product. You are not changing the product design that frequently. Another kind of layout is a process layout. Essentially, a process layout is something where you have different departments, let's say A, B, C, D, E, F. Each of these departments houses machines which are similar in character, though these machines are not identical. For instance, A could be all the lathes. So lathes with different features are in the lathe shop. This could be a milling shop, this could be a grinding shop, and so on. So each shop has different types of machines clubbed together. And what happens is that a particular product, depending upon its requirements, will move from one department to another till finally the product is produced. So the major advantage of this type of layout is the product variety that it can handle, unlike the product layout which typically handles a single type of product. So you can make a variety of products in this particular layout, and of course what will be the major problem here? The major problem will obviously be large number of products moving here and there, so there will be a lot of confusion in terms of movement. There will be lot of delays as products wait and move to different departments. Therefore the production times generally tend to be large in such situations. Of course, you could try to have a situation where you have both the product and the process layouts mixed. So it's a mixed layout. A mixed layout is a very common layout in industry. For instance, what would happen is that if you go to a factory like Maruti Udyog, for instance, you would find that the final product is being produced on as an assembly line. So it's a product layout, but the various components which go into the product are actually being produced in a process layout in different shops. So you invariably have a mixture of both the product and the process layout in various organizations. And of course, one can also talk about a cellular layout or a group layout, which is something that is generally suited to a situation where you have a predictable variety of products to make, and the idea is that you try to group or products into product families, parts into part families, and these individual parts or part families are then subjected to processing in individual cells. And the basic idea is that in a cell the processing sequence is almost uniform. So the motivation behind the cellular layout is that we try to get the advantages of both product layouts and process layouts. That means you get the variety of the process layout, and you try to get the speeds by this grouping of parts which are all then processed in various kinds of cells. And then we talk about layout by fixed position. In a layout by fixed position, what happens is that the layout is determined by the size of the product. For instance, this is true for special structures or for shipbuilding or for assembly of an aircraft. Depending upon the type of the aircraft, you have different machines, different people keep coming and moving. So in all these cases what was happening was that the job was moving and the machines were stationary. Here the job is stationary and the machines are moving. So there is really not much to choose as far as the layout is concerned. This is governed by the shape of the product itself. If you are building a ship, the shape of the ship itself will dictate the layout, and machines will come, do the welding operations or the riveting operations and go back, and then somebody else will do the painting and this and that. So this is what it is. We are looking at this layout design problem. It's important to note how this problem is actually affected by other decisions pertaining to the product, the schedule and the process. You see that the layout design problem which we are trying to address is governed by the product design, the process design and the schedule design. That is, the product design means what you have to make. That determines the layout. How you have to make it, that means the process that you have selected for making the product. So this will determine the various machines and equipment that you need. And schedule design, which talks about how much you need to make. So this is essentially a decision that comes from marketing, forecasting of demand, which tells you how many pieces you need per day. So the product, process and schedule constitutes the basic information that you need for layout design. So, and mind you, it's not only layout design which is linked to these, but these decisions in themselves are also related to each other, because the choice of the product will also determine what process to take. Choice of the process will also determine the schedule that you have to follow, and so on. So in the layout design process, we are here primarily talking about the layout of process layouts. In the layout design process, you need inputs from the product, the process and the schedule. That's the important thing. If you try to compare, for instance, what would be the features of a product layout in this category, you find what is a product layout. A product layout is a situation where the input is some raw material and it is being processed on different workstations in sequence till finally the final product comes out here. So in a situation like this, you have smooth and logical flow lines. You need to have very small in-process inventories, because the part which is processed here will immediately go to the next machine, so there has to be very little in-process inventory here. Total production time per unit is short. There is reduced material handling because the parts directly move from one workstation to the other, so it doesn't have to be transported in trolleys and trucks to other departments. There is little operator skill and the training is therefore simple. Simple production planning and control, and there is less space for work in transit and temporary storage. So these are some of the features of a product layout. Let's look at a process layout now, which is our basic concern in this particular session. A process layout is a collection of departments A, B, C, D, E, F, which are housed in maybe different rooms or different buildings. And therefore the advantages are that there is better utilization of machines, hence fewer machines are needed. Why does this happen? Because here you have a lathe, let's say a special purpose lathe, you have it here once. So all jobs which require processing on that special purpose lathe will come here and get the processing done and go away. Whereas if the same thing was to be done in a product layout, you will have to duplicate the machine at whatever operation it came. If you need a lathe here, after 10 operations you require the same lathe, you duplicate it. So generally better utilization of machines and fewer machines are needed in a process layout. There is a high degree of flexibility with regard to equipment or manpower allocation for specific tasks. What does this mean? If a job comes to a department of the milling machines, there is often a choice. It can be put on either machine 1 or machine 2 or machine 3 because they are all capable of doing the operation, and it can be given to different operators depending upon their skills. So you have this flexibility with regard to both equipment and manpower allocation for specific tasks. Comparatively low investment in machines is required. This follows from 1. There is greater job satisfaction for the operator. Why is there a greater job satisfaction for the operator? Because the operator who is working in a particular department during the day handles a variety of jobs, different types of jobs. Unlike an operator, let's say, who is working on a product layout, who would be sitting on a machine and operating a pedal. So he operates the pedal maybe 250 times a day, and that's the end of his life, right? So here there is greater job satisfaction for the operator, and specialized supervision is also possible here. Why specialized supervision? Because the supervisor for the lathe section may have spent 10 years in the lathe section and become a supervisor, and he now knows the ins and outs of all the machines which are there in this particular shop. Whereas if you talk about a product layout on a line, there are different machines manufactured by different manufacturers and having different features. It is impossible for one particular individual to be an expert of all those machines. So the kind of supervision that he would be able to give is only general and not specialized. However, the process layout has some limitations too. We should be aware of those limitations. Since longer flow lines usually result, material handling is more expensive. Obviously, a part has to go from here to here, so it has to first wait, then somebody has to load it onto a trolley, and then the trolley has to go. The trolley may wait in that department till somebody unloads it, and so on. So longer flow lines usually result, material handling is more expensive. In fact, the general objective function in designing a layout of this type is, one of the major objectives is to minimize the material handling cost. Production planning and control systems are more involved in such systems. Total production time is usually longer. Large in-process inventories take place because material might be stored up in different departments without being processed. Space and capital are tied up by work in processes. And because of the diversity of jobs in specialized departments, higher grades of skill are required. This is also another feature, because quite often if you need somebody to operate a grinding machine, you would at least expect that he has done an ITI diploma and has put in 3 years before he can undertake to operate such sophisticated machines. So all these operators operating these machines would generally be people who have higher grades of skill, unlike an operator on a product line. Because on a product line, even if you select a man from the street, all he has to do is to press a pedal 250 times, and that practice can be given to him in half a day. And therefore training people in product for operating product layouts is generally much easier, whereas here it will be much more difficult. Let us look at this chart, which is called a PQ chart. And essentially what we have said is that if you have to make a large number of products, so P is the product variety, and we arrange these products in the descending order of the quantity that you need. So what really happens is that this product, the first one, is to be made in large quantities, this product is to be made in lesser quantities, and so on. So we have products which are arranged in the descending order of their quantity. Now this chart, which was suggested by Muther, it gives an idea of for the situation under which you should use different types of layouts. For instance, what they said is that once you got these products lined up like this, the products which are here, that means for products for which the variety is low but the quantities are high, those are the products for which a product layout is most suitable. That means you should set up an assembly line. And on this end here, where you have a large number of products but the quantities are relatively smaller, so it's a large amount of variety but low production quantities, this is the situation where a process layout is recommended. And in between these two categories, when you have intermediate variety and intermediate production quantity, generally you would use a combination layout, which is the product of these, this and this. The idea here is only to give you a overall intuitive feel of when a product layout and when a process layout should be selected. A product layout is most appropriate when you are having fewer number of products to produce in large quantities, and a process layout is used when you have large variety but to be produced in small quantities. So I think this summarizes the features of product and process layouts in that sense. Let us now look at the process of designing a process layout. Normally when you talk about layout planning, we are generally talking only about process layouts, because product layout, the layout is generally fixed by the sequence of operations, so there isn't much to design except to ensure that you have the space to lay out those machines. So there is a procedure which is called systematic layout planning, SLP. SLP procedure of Muther, proposed way back in 1961, where he gave a general framework for how these process layouts are to be designed. You might wonder as to why a procedure developed so long ago is still being talked about. You talk about something when it is still useful. The zero invented so many years ago is still useful, isn't it? So that's of course one thing. But the point here is that the systematic layout planning procedure of Muther has suddenly become important, because this has now become the basis for many of the computerized layout planning algorithms which are available. In the next class, we shall be talking about some computerized layout planning procedures, and those procedures are actually basing their inputs and operations on the SLP procedure. So we look at the SLP procedure in this class to understand what all is required. For instance, the first thing that is required is to input data and activities. Now what is the kind of data or activities that you have to input for this particular problem? There are three kinds of data that you need to input: the product data, the process data, and the schedule data. We talked about this. So the input to the process of planning a process layout is essentially inputting this kind of data about the product, the process, and the schedule. And from this input data, the first step that is done is to identify the flow of materials. The second step that is done is to identify the activity relationships. Based on step 1 and step 2, we develop what is called a relationship diagram, and then this relationship diagram is converted into what is called a space relationship diagram. In order to develop the space relationship diagram, you have to compute in step 4 the space required, match it with the space available. That means if you find that the space required is 4,000 square feet, you must make sure that 4,000 square feet of space is available. So it's just a check in that direction, and then you develop the space relationship diagram in step 6. This space relationship diagram is then subjected to modifying considerations and practical limitations which you may not have considered in the entire process so far, and on the basis of this you develop the layout alternatives. You evaluate these alternatives and pick up the best layout alternative that you have. So this is the broad framework, and it's a very systematic framework for a problem like designing a layout. You can see that you can divide this framework into 3 different phases. Up to here is the phase of analysis, right? Up to step 5 is the phase of analysis, where you are analyzing your data, finding out the flow of materials, the activity relationships depending upon the activity relationship diagram, the space required and the space available. And once the analysis part is over, you look for a search for the solutions. So from the space relationship diagram, you are developing layout alternatives. So you are searching for alternative solutions, and then once you have searched you have developed these solutions, you have to identify which is the best. So it is the selection of these solutions. So search followed by selection preceded by analysis is the general order of this particular algorithm. And one reason why it is popular is that it provides a framework for, it tells you exactly what is to be done. And when you are developing a computer program, you must tell the computer exactly what is to be done, and that is why this framework has been used in layout planning exercise. So this is the SLP procedure of Muther. Now we will try to illustrate this procedure to a sample problem so that you get an idea of what exactly or how the layout operations can be done. Now just to give you a feel, if we were to organize production as a product layout, essentially what it means is that you have to start from the raw material stage. So you have different types of products. You go to the saw department, you go to the milling department, you come to inspection 1 and then do this operation here, do this operation here, and then final operation here, and you come out, and similar. So basically what we are trying to say is that these very departments which are laid out could also be laid out so that you are trying to facilitate a product layout for 3 different products in that sense. Okay. Now in this particular scheme of things, we have essentially used these 3 symbols. The circle represents an operation being done, like a machining operation or metal removal or grinding or whatever. A square represents an inspection, and a inverted triangle of this nature represents storage. So just a convenient way of representing the various types of operations which are required here. Let's assume that we have a process layout for the same thing. So what we have is, we have these different departments: raw material storage, saw department where sawing is done of the material, the lathe department, the drilling department, the milling department, the inspection, the packaging and finished goods. And here again we have different products which we try to move. So these products move according to their needs, so there is a lot of crisscrossing. So typically this is the kind of thing that happens in a process layout.
What are the crosses that have been made?
These crosses,
Yes.
I think these crosses are supposed to be the centroids of these individual departments. So if you have a raw material store, this is the center. If this is the one, this is the centroid, this is the centroid, this is the centroid. We will need them later. Let's suppose that we are trying to work on this particular process layout, and we are maybe trying to evaluate this process layout, or trying to find a better layout by using SLP. So we'll see how we can do that. So the operation would be something like this. This is our input data for the problem. We are saying essentially that there are 3 products A, B and C which we want to manufacture, and the processing sequence of these products is, this first goes to saw, then mill, then inspect, then turn, then mill, then drill, then inspect, then package, and similarly for this, and similarly for this. That means we know for each product the processing sequence. So we know the information pertaining to the product, what is the product and how it is going to be processed. Product and the process information is available to us for these three products. Then we would also like to know the schedule information as to how much is the demand for each of these products. Now what might happen is that these products might be varying considerably in sizes. This might be a small casting, this might be a much bigger thing, this might be a smaller thing, and so on. So in order to take care of that aspect, what we are simply saying is we are standardizing the material flow required in the plant to pallet loads per day. That means how many trolley loads per day will be needed. So what we are saying is that as far as product A is concerned, we require 8 pallet loads per day in terms of production. This might be something like 160 products or whatever it is, but we are talking in terms of pallet loads. Similarly, B requires 3 pallet loads, which might be 300 components or whatever, it could be different, and C could be 5 pallet loads per day. So we are using a common unit for measuring the material handling of these products throughout the plant. So this is essentially our schedule requirement as to how many trolley loads of A, B, C must be produced per day in the factory. So we need information about the processing, the products, the processing, and the quantities. So this is the input to the thing. Now what we are going to do is we are going to actually construct what is called a from to chart. And a from to chart is actually a convenient means of reducing a large volume of data into a workable form. And by inspecting the data displayed in the from to chart, the layout analyst can identify the departments having large volumes of movement. So let's try to do it for our example. What we find here is, let's say how you construct this information. A from to chart is actually a square matrix, and in the matrix we have listed all the departments: raw materials, saw, lathe, drill, mill, inspection, packaging, and finished goods. So same departments here, and so on. So what we are trying to basically find out is what is the total movement from these to this. So it's a from to chart. It's very much like a distance chart, which you say what are the distances from one pair of cities to another pair of cities. For instance, what you find is that everything begins from the raw material stage, right? So you have what we have is what is the total movement which will take place from raw material to saw. So what you are seeing is, let's look at this requirement. This product A will go from raw material to saw, C will also go from raw material to saw, but B will go from raw material to drill, it doesn't go to saw. So as far as this is concerned, products A and C will make a movement from raw material to saw, and you can easily find out what is the total movement of raw materials of products A and C. So A is 8 trolleys are moving and C is 5 trolley loads are moving. So 8 plus 5 is 13. That's how you get this figure of 13. And similarly for the other entries in this particular chart. So what it shows is that the total movement which takes place from raw material to saw is 13 trolley. Daily there will be 13 trolley loads moving from raw material to saw, right? And from raw material to drill 3 will be moving. And as far as this movement is concerned, from milling to inspection 16 will be moving, and so on. So this from to chart shows the number of material handling trips per day between all the departments. Now what we want to basically do is, what is the idea? The idea is that those departments which have a large amount of movement, especially these departments, should be as close to each other in the layout as possible. That is the basic idea. They should be as far as possible close to each other, and for those departments which don't have any movement, they need not be that close in that sense. So from this from to chart, we can make a comment like this. Normally the from to chart is used to analyze the flow in process layouts. The item movement that occurs over some specified period of time is totaled for all the products and entered in the from to chart as shown in the next figure. What we would like to simply show is this information. In this figure, which is also a from to chart, the previous chart was total flow or material handling or material flow taking place between all pairs of departments. This particular chart is the information pertaining to the distances between these various departments. You were asking me about the centers in that layout. So if we are now talking about this layout, we look at the centroid of each department and find out what is the distance from the centroid of one department to the centroid of the other departments. So on that basis we can construct a diagram of this nature which would show that the material raw material to drill department is 72, and notice that this is the various distances between all pairs of departments are listed here. This particular matrix could be either symmetric, but it's not necessary that it be symmetric, because the distance from one department to another need not be the same as the distance from the same department back itself if there are unidirectional flows and so on. But if you are permitting all kinds of flows, then this may be the same. Okay, so whatever be the distances, they can be accommodated, and this is the distance matrix. So we have a flow matrix and we have a distance matrix which we have now constructed. The important thing to note here is that the distance matrix can be constructed only if you have a tentative layout. So it is for that tentative layout that we have made the distances. So then what we do is we multiply the two matrices element by element. So now we have the total material handling effort. So this is the total loads multiplied with the distance which we had in the previous matrix. So we have two matrices, we multiply that. So this is the total material handling effort, total material handling effort. So you will have these entrances here. We can sum up the rows. You will get the 424 is the material handling effort. So total material handling movement from the raw material is 424 units, and total material handling movement to the saw is 208. So this is the to and this is the from in terms of total material handling effort, and a 0 in a particular column shows that this is a source, and a 0 in a particular row shows that this is a sink, obviously, because what's happening is that everything flows from the raw material store, so it's a source, there's nothing coming to it, and the finished goods is the last operation, so that's where you have it, nothing goes out of it in that sense. So if you sum up these values, this column or this row, the total value is 4032. So it shows that the process layout which we are at the moment investigating has a total material handling effort of 4032. This is a significant development, because what have we done? We have been able to quantify the material handling movement for a layout, and this is like the objective function for that particular layout. So we have been able to say that the total material handling effort for this layout is so much. Clearly we could use this information to evaluate different layouts. I mean, if plan 1, plan 2, plan 3, each one we can calculate, the distance matrix will be different, the load matrix will be the same. So you will get different material handling figures, which is like the objective function values, and you can choose that particular layout which in fact has the minimum material handling effort. And in fact this is one of the basic logic that is provided in the development of craft, which is a computerized relative allocation of facilities technique, which we can talk about in the next class. Now, what we can how we can plan a layout by following these steps is something like this. Suppose these were the departments which were to be placed in a layout: the office, the foreman's office, the conference room, the parcel post, the path shipment, repair and service area, receiving, testing and general storage, say. The first thing that you can do is, apart from the material handling effort, you see, we were there talking about box number 1 in the SLP procedure, that is development of the flow of materials in the various matrices. We are now talking about box number 2, where you are trying to develop activity relationships for these things. So what you can say is, for instance, for each pair, for instance, you can say that as far as repair and service parts is concerned, its proximity to, for instance, the conference room is unimportant. So we give a U rating here. So this is the significance of the U. You have various ratings. Normally what we give is, we give typically the ratings A, E, I, O, U and X. What this means is, A means it's absolutely essential to locate the departments close to each other. Okay. For instance, this is A. It shows that parts shipment and general storage, it's absolutely essential to have them close to each other. So you have an A rating. E means it is essential, but not absolutely essential. So for instance, service area and testing, it's essential to have them close to each other. I is important. So for instance, here the conference room and the foreman's room, it is important to have them close to each other, because you can call them for conferences or whatever be the reason. O, ordinary closeness is okay. So you have an O rating between the repair and service department and the parcel post. And U is unimportant. It's unimportant that they be close to each other. For instance, conference room, it is unimportant that it is close to parcel post or path shipment and so on. X means it is highly undesirable to have these two departments close to each other. You don't see that here, but what may happen is, for instance, you might want you might have a foundry. You might not want that to be close to your air conditioned metrology shop. So you can give an X rating, that is highly undesirable to have these things there. So what is really important is, in giving these ratings, for these are giving the general preferences that you may have for locating certain departments close to each other or not. So you accommodate those priorities that you have in the form of these ratings. These are called activity relationships.
So there are some numbers also in that class. So what are those numbers?
The numbers are normally given because a factor, say E, you might have a number of reasons, 1, 2, 3, 4, 5, which you document. So for convenience, we might refer to for what reason we identified E. That's it. Okay, when you are documenting this. Yeah, the numbers are also clear here. Basically, the question that you are asking, when we are talking about these ratings, absolutely essential, especially important, important, ordinary closeness okay, U unimportant and X is undesirable. And when you are giving any rating, it could be for various reasons for which you could give a code, like flow of materials, ease of supervision, common personnel, contact necessary, convenience or something else. So when you give a rating, you might see whether it is for this reason or that reason or whatever. That's the idea. On the basis of this information, we can develop what is called an activity relationship chart. This is what an activity relationship chart looks like. We have these departments from 1 to 10 which we were talking about. So each square represents a department 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and each department, after being represented by a square, you identify what kind of a rating you want to give between these departments. Like we said, activity rating. Mind you, the rating can also consider the material handling effort which you computed in step 1, right? So you can have various types of situations. Say it should be 1 line here, 2 lines here, 3 lines here, and 4 lines here, let's say. And u is no relationship, and x rating could be a wavy diagram. So what will happen is, for instance, between 1 and 3 there are 3 lines. It means that there is an E rating between 1 and 3, and similarly for the others. So what will happen is that the number of lines between a department actually shows the affinity between these departments. That is, the relative desirability of different departments to be close to each other is stronger if the bond is stronger, and the number of lines show the bond. So you are basically getting an idea of which department should be kept close to each other through this. This is called an activity relationship diagram. Now here we had assumed that the same size was there for department, but you have to calculate the requirements of each department. So what will happen is, typically, how will we do that? For different departments, say if this is the saw department, you know that it houses this equipment, the Armstrong hacksaw, and there are 3 of these. The machine center dimensions for each of these in feet is 10 by 9. So the total machine area requirement is 190 per machine, and the total process area required is, because there are 3 machines, 570 square feet. So you can find out immediately the amount of machine area that you need for this department called saw. Similarly, in the mill you might have different types of machines. You have a plane mill, 5 of them, vertical mill, 7 of them, hand mill, 4 of them. You know the department sizes of the machine center requirements, area of each department, and the total area corresponding to each of these machines. So this exercise can be done for the calculation of the production space. So we do it for each department in a same manner, and at the end of it we have been able to find out the total. That means the final area requirements, the total square feet required is now 3931, but this is the space required only for the machines. So normal practice in factory design is to add 40% space for aisles, that is the movement within the department. So 40% aisle space of this, 40% of this is 1572. So the total production space required is 5503. That is how we calculated this space, and we also know the space requirement of individual departments as a consequence. So we have so far not considered non-productive activity space. This was only production space. So you will have to add the requirements of the non-production activity space for storage, office, locker rooms, foreman, maintenance, tool crib, and so on. And this total area comes out to 1448 square feet in addition to the one that we already had. So we'll have to add to the earlier area, production area 5503, this additional space of 1448, and get the total requirement of 6951 square feet of floor space required in total. So this is the activity involved in calculating the space from the production requirements and the non-production requirements. What is then finally done is, we had the activity relationship diagram. The activity relationship diagram, each department was shown as a square. This is called a space relationship diagram. We did the calculations for the space. Now each department is shown proportional to its size. This department had a size of so much, this department had a size of so much, and so on. This was a bigger department, it has a size of 1750, and so on. So you represent these departments in terms of sizes proportional to their areas. So you know this. So what is the problem now? if you can imagine that these were individual blocks cut out of cardboard with various things, you could shift them around and try to arrange them in the form of a layout, and you would then ultimately get a layout. This is basically what many of the computer programs do. They begin with this diagram as an input and then try to generate different, by shuffling around these departments, generate a layout. Obviously there are infinite possible combinations, so you have to look for a best combination, and best means what is your objective. The objective could be anything. Generally the objective is material handling effort, but if you are using activity relationships, you are trying to maximize the material handling and other factors also, because what you do is you can give some weightages to A, E, I, O, U, X, some marks, and ultimately develop a layout for those particular marks, right? So finally what we do is we can develop a plant layout by shuffling these departments, and ultimately this shuffling leads to what is called a block plan. So this is the block plan which shows department 1 should be here, 2, 3, 4, 5. So we have actually solved the plant layout problem for this particular case by developing a block plan which looks like this. And finally, when we look at the what we have tried to do in this particular lecture, we have seen that the objectives in different types of layouts, whether you're talking about process layout or product layout or mixed layout or even cellular layouts, the objectives are different, and therefore the ways of handling these layouts are all different. Systematic layout planning is a systematic procedure for designing process layouts, and basically we looked at this procedure in this particular class to identify, see how systematic layout planning can be done for process layouts. From 2 charts to measure material handling effort were designed, and a step-by-step procedure for a sample layout was done, and the major advantage of this particular systematic layout planning procedure is that it is a precursor to computerized layout planning. And therefore in the next class we will try to look at some of the computerized layout planning procedures that are available for handling the layout planning problem. Of course this will constitute a basis for doing the exercise.